Hello everyone, welcome to another week of space exploration, Geography 2090, space exploration, Space 2090, whatever you want to call it. This week we're learning about everything that happened before the space age. So a couple things to unpack there. First of all, when did the space age start? And what are we studying that happened before this mythical date? So the beginning of the space age, for the most part, is typically identified as October 4th, 1957. That is the day that the Soviet Union launched Sputnik into orbit. So the first human-made object, which was a little sphere, a tiny little satellite that we'll learn about next week, it was put into orbit around the Earth. And it was the first time that humans had created something, put it into Earth for the purpose of studying outer space. Now, Sputnik didn't really teach us much about outer space, other than that we could put something in orbit around the Earth. But I would say a vast majority of books you read or documentaries you see or movies you see will use the launch of Sputnik as the beginning of the space age. But that's the beginning of humans actively putting things in space, eventually ourselves into space to learn about space. But before that, we'd still been, if you want to call it exploring space, we'd been thinking about space, studying space from Earth without actually going to space, whether we were putting a thing in space or putting ourselves in space. We were still studying the nature of Earth and what is surrounding Earth and what is the origin of Earth, which we won't get into really in this course beyond the formation of the solar system, which we've already learned about. But people were already thinking about space or the solar system. They may not have always used the words we use today for these things, but as you'll see, the Earth being a spherical object, the Earth going around the sun not being the center of the universe, the Earth not being the center of the universe, orbits, planets, moons, all of these things had already been understood before we went to space. So we weren't starting in 1957 from scratch, not knowing anything about space, but we just were now up close and studying it in a little bit more detail. So for the rest of this video, we're going to learn about, in a really rushed way and with selective examples, because it would be impossible to cover the entire of antiquity and the understanding of space across all times and cultures. I'm going to focus on a few key examples from around the world of what we knew or learned about space, as well as a little bit about space technology, rockets. We'll talk about those for just a sec, so that going into next week, we understand that, yes, the space age started October 4th, 1957, but humans weren't starting from scratch. We already knew a little bit. So, to start off, I want to get to one of the bigger misconceptions that exists about the pre-space age, and that's that humanity was unaware of certain aspects of the solar system until the time of Galileo or Copernicus. Simply put, this isn't true. A lot of ancient thinkers across multiple different cultures had come to conclusions about things like the Earth being round, heliocentrism, and even the possibility of other planets. One of these important thinkers was Philolaus, a 5th century BC Greek philosopher from before the life of Socrates. As far as what has been recorded or physically documented historically, Philolaus was possibly the first person to write publicly that the Earth was not at the center of creation, but instead that our world revolved around a central entity, or what he called a great fire. Now, oddly, Philolaus may not have necessarily been talking about the sun when he said great fire, but that's neither here nor there. What's interesting is that unlike future claims about the Earth revolving around the sun, Philolaus's ideas didn't cause much controversy. Unlike in cultures dominated by Abrahamic religions, Greek philosophical views of the cosmic order didn't run counter to pagan beliefs as much as we will see with future thinkers in the West. Now, someone else to talk about in the vein of understanding space before humans ever went there is Aristarchus of Samos, a Greek astronomer who several hundred years after Philolaus added the idea that the sun was the center of the system of which the Earth belonged, essentially the notion of heliocentrism. That the Earth orbited around the sun was the central thesis of heliocentrism and remains so today. While Aristarchus was wrong about the sun being the center of the universe, heliocentrism would continue as a dominant astronomical concept until the fall of the Greek and Roman empires, where it would fall out of favor. We'll hear about that later. This brings us to Lucretius, a Greek philosopher who is important, if for nothing else, for his influence on future thinkers like Giordano Bruno. Lucretius actually argued against many of the things of his time because he did not accept that the Earth was a sphere. He instead promoted the idea of an infinite world. While Lucretius was very wrong about the nature of our planet, he was one of the loudest voices of his time to advocate for an infinite universe, a concept still engaged by modern cosmologists. Now, Western thinkers are not alone in conceptualizing aspects of our solar system. Aryabhata, a 5th century Indian mathematician, correctly postulated that the Earth was both a sphere and that the cycle of day and night, as it occurred differently on different parts of the planet, was explained by the Earth rotating about its axis, so the Earth spinning. Aryabhata also postulated the number of planets and order of much of the solar system, and while he was wrong about the distance and relative locations of the planets, and he could not have possibly known about anything beyond Saturn, he started down a path that later mathematicians and philosophers would use to develop accurate descriptions of the solar system over a millennium later. Finally, we have to also mention Arabic philosopher Avampas. Avampas built off of all of these previous ideas to advance the notion of a system of planets that operate in a predictable and relational manner. Now, gravity was not a concept being used to explain this predictable and relational manner, but once gravity came into the equation later on, it would help us understand that Avampas was very much onto something long before even Copernicus and Galileo. He also hypothesized on the nature of the broader galaxy and existence of other solar systems. Avampas was part of the golden age of knowledge in Islam, in which hundreds of revolutionary ideas in mathematics, physics, and astronomy were developed across the Arabic and wider Islamic world between the 8th and 14th century. Other major astronomers of the golden age include Abu Rayyan al-Biruni and Nasir al-Din al-Tusi, who advanced notions of planetary motion, physical constants, and the relation between objects and the universe. Now, of course, I can't mention every important thinker of the ancient world in this summary, but I hope you appreciate that from these examples, that notions of the Earth's rotation as a sphere and its orbiting the sun are not as recent as the European Enlightenment as a lot of us learned in grade school. But these are mathematical concepts that were correctly postulated by thinkers across numerous ancient cultures over 2 millennia ago. Now, you might be wondering, how exactly did these ancient figures figure out some of these things? Well, the specific mathematics aren't the focus of this course, though many of you probably did learn about the methods these thinkers used when you studied geometry in high school. Now, before we move forward, let's take a look at one example of how Eratosthenes, who I haven't mentioned, not only correctly identified that the Earth was spherical, but also got a pretty good idea of how big our world was.
There was once a time when our little planet seemed immense, when it was the only world we could explore. Its true size was first worked out in a simple and ingenious way by a man who lived here in Egypt in the 3rd century BC. This tower may have been a communications tower, part of a network running along the North African coast, by which signal bonfires were used to communicate messages of state. It also may have been used as a lighthouse, a navigational beacon for sailing ships out there in the Mediterranean Sea. It is about 50 kilometers west of what was once one of the great cities of the world, Alexandria. In Alexandria at that time, there lived a man named Eratosthenes. One of his envious contemporaries called him Beta, the second letter of the Greek alphabet, because he said Eratosthenes was second best in the world in everything. But it seems clear that in many fields, Eratosthenes was alpha. He was an astronomer, historian, geographer, philosopher, poet, theater critic, and mathematician. He was also the chief librarian of the great library of Alexandria. And one day, while reading a papyrus book in the library, he came upon a curious account. Far to the south, he read, at the frontier outpost of Syene, something notable could be seen on the longest day of the year. On June 21st, the shadows of a temple column or a vertical stick would grow shorter as noon approached. And as the hours crept towards midday, the sun's rays would slither down the sides of a deep well, which on other days would remain in shadow. And then, precisely at noon, columns would cast no shadows, and the sun would shine directly down into the water of the well. At that moment, the sun was exactly overhead. It was an observation that someone else might easily have ignored. Sticks, shadows, reflections in wells, the position of the sun, simple, everyday matters of what possible importance might they be. But Eratosthenes was a scientist, and his contemplation of these homely matters changed the world, in a way, made the world. Because Eratosthenes had the presence of mind to experiment, to actually ask whether, back here, near Alexandria, a stick cast a shadow near noon on June the 21st. And it turns out, sticks do. An overly skeptical person might have said that the report from Syene was in error, but it's an absolutely straightforward observation. Why would anyone lie on such a trivial matter? Eratosthenes asked himself how it could be that at the same moment, a stick in Syene would cast no shadow, and a stick in Alexandria, 800 kilometers to the north, would cast a very definite shadow. Here's a map of ancient Egypt. I've inserted two sticks, or obelisks, one up here in Alexandria and one down here in Syene. Now, if at a certain moment each stick casts no shadow at all, that's perfectly easy to understand, provided the Earth is flat. If the shadow at Syene is at a certain length, and the shadow at Alexandria is the same length, that also makes sense on a flat Earth. But how could it be, Eratosthenes asked, that at the same instant there was no shadow at Syene and a very substantial shadow at Alexandria? The only answer was that the surface of the Earth is curved. Not only that, but the greater the curvature, the bigger the difference in the lengths of the shadows. The sun is so far away that its rays are parallel when they reach the Earth. Sticks at different angles to the sun's rays will cast shadows at different lengths. For the observed difference in these shadow lengths, the distance between Alexandria and Syene had to be about 7 degrees along the surface of the Earth. By that I mean, if you imagine these sticks extending all the way down to the center of the Earth, they would there intersect at an angle of about 7 degrees. Well, 7 degrees is something like a 50th of the full circumference of the Earth, 360 degrees. Eratosthenes knew the distance between Alexandria and Syene. He knew it was 800 kilometers. Why? Because he hired a man to pace out the entire distance so that he could perform the calculation I'm talking about. Now, 800 kilometers times 50 is 40,000 kilometers. So that must be the circumference of the Earth. That's how far it is to go once around the Earth. That's the right answer. Eratosthenes' only tools were sticks, eyes, feet, and brains, plus a zest for experiment. With those tools, he correctly deduced the circumference of the Earth to high precision, with an error of only a few %. That's pretty good figuring for 2,200 years ago.
We jump forward in time to a place where many of us raised in North America picked up the story of the solar system and basic notions of astronomy. And while this is often where stories of Western astronomy start, it's important to remember the figures we discuss next are not introducing universally new ideas as much as reintroducing old ideas that had fallen out of favor with religious or even secular world orders of their time. So yes, now we start with Nicolaus Copernicus. Born in 1473 in what is now Poland, Copernicus was a Prussian cleric who lived during the European Renaissance and whose life would kick off a revolution in Western science named after him. With 1,000 years having passed since much of the advancements of those ancient thinkers I just mentioned, heliocentrism had actually fallen out of favor, or in many instances, it had never been truly taken up by the public or rulers of Europe in Copernicus's era. Indeed, by the time Copernicus had finalized much of his thesis on the orbit of the planets around the Sun, as well as the Earth not being the center of the universe, he had become skeptical about making his writings public, either because he feared public backlash or due to his own reservations about the ideas. After being pressured by colleagues, Copernicus did eventually allow his magnum opus, De Revolutionis Orbium Celestium, or On the Revolutions of the Celestial Spheres, to be published. However, by the time the pages were being printed, Copernicus was on his deathbed. Some of the key concepts in Copernicus's work were as follows. The Earth was not the center of the universe. All the planets of the solar system orbit the Sun. The distance between the Earth and the Sun is much greater than people have assumed, and the Sun's apparent motion through the sky is actually the result of the Earth's motion and not vice versa. Before his ideas could catch on, Copernicus died in 1543. With Copernicus dead, his ideas didn't actually cause as much of a controversy as he might have worried. It wouldn't be until another great astronomer, or two, would champion Copernicus's ideas that a great battle would ensue between science
in the air.
Born 21 years after the death of Copernicus, it was Galileo Galilei, an Italian astronomer and physicist, who took up many major ideas from the ancients and began a battle between geocentrism and heliocentrism. In Galilei's time, heliocentrism had again fallen out of favor with the educated classes and the church, which mostly overlapped. Galilei aligned with ideas from the past, such as those of Aristarchus and Copernicus, and he argued with contemporaries, such as fellow astronomer Tycho Brahe, that the movement of the Earth around the Sun was consistent with modern observations, and that the accepted ideas of geocentrism failed because they assumed the Earth and the Sun were too close together. Galilei was more outspoken, even brash about his ideas than Copernicus was, and he wrote prolifically on the subject. Eventually his writing was submitted to the Roman authorities under the auspices of blasphemy in 1616. The hearing decried heliocentrism as nonsense and forbade Galilei from continuing to write about it. Galilei obediently avoided the subject for a better part of a decade, only taking it up again when asked by none other than Pope Urban VIII in 1623 to include the debate over heliocentrism in Galilei's forthcoming writings. Urban VIII was an admirer of Galilei and appreciated theological debate that included the insights of science. Galilei's writings turned into the book Dialogue Concerning Two Chief World Systems, and despite Galilei's intention not to openly advocate heliocentrism, the book was decried as outright heresy. Galilei was tried for heresy, and with Pope Urban unknowing or unwilling to intervene, Galilei was sentenced to a life of house arrest, where he stayed until his death in 1642. The magnitude of Galileo's discoveries beyond advocating heliocentrism are also important. Many of his observations of the solar system are surprisingly accurate, including the size and dynamic nature of the rings of Saturn, the phases of planets as they orbit the Sun, and his discovery of the major moons of Jupiter, Io, Callisto, Europa, and Ganymede. Just as Galilei had built off Copernicus and the ancients before him, more great astronomers, physicists, and mathematicians from around the world were just around the corner to build off of Galileo's work. As the European Renaissance gave way to a 17th century scientific revolution, world-changing ideas would emerge and lead directly to principles of planetary motion critical to ushering in the space age 3 centuries later. The most important of these ideas was gravity. Now, we're not going to get into Isaac Newton and gravity in great detail, but throughout the rest of the video, we'll see some of Newton's most famous thought experiments carried out in order to explain some of the fundamental concepts of gravity necessary for space exploration.
This is NASA's Space Power Facility near Cleveland, Ohio, and it is the world's biggest vacuum chamber. It's used to test spacecraft in the conditions of outer space, and it does that by pumping out the 30 tons of air in this chamber until there are about 2 grams left. And it's kind of got an eccentric construction, which is part of its history. It was built in the 1960s as a nuclear test facility to test nuclear propulsion systems, and that meant that they built it out of aluminium to make the radiation easier to deal with. Aluminium is not the best thing, the strongest material to build a vacuum chamber out of. So they built an outer concrete skin, which is part radiation shielding and part an external pressure vessel, so that this thing can take the force that's present on the outside when it's pumped out to the conditions of outer space. Galileo's experiment was simple. He took a heavy object and a light one and dropped them at the same time to see which fell fastest. Now in this case, the feathers fell to the ground at a slower rate than the bowling ball because of air resistance. So in order to see the true nature of gravity, we have to remove the air. It takes 3 hours to pump out the 800,000 cubic feet of air from the chamber.
Okay, we dropped 2 millitorr in the last 30 minutes.
But once it's complete, there's a near perfect vacuum inside.
6104 manual, 10% open. Station 1, go for drop. PCB 30-1, pressure set point at 240 psi. We are go for drop.
10, 9, 8, 7, 6, 5, 4. Cameras on. 2, 1. Release.
Exactly. They came down exactly the same. Wow.
Look.
That's right there. Look at how they hit right there.
Exactly.
You're back on the side.
Exactly the same.
Feathers don't move, nothing.
Look at that. That's just brilliant. Isaac Newton would say that the ball and the feather fall because there's a force pulling them down. Gravity. But Einstein imagined the scene very differently. The happiest thought of his life was this. The reason the bowling ball and the feather fall together is because they're not falling. They're standing still. There is no force acting on them at all. He reasoned that if you couldn't see the background, there'd be no way of knowing that the ball and the feathers were being accelerated towards the Earth. So he concluded they weren't.
Johannes Kepler was a German astronomer and teacher who actually worked for Tycho Brahe. Remember him as one of Galileo's sparring partners over heliocentrism. Kepler's timing was important because it allowed him to break free from some of the more careful exploration that his precursors had to live with when writing about their research, including Brahe and Galilei. Kepler was in no way anti-religion, but he did find a way to advance scientific theories of the solar system without entirely disrupting the church or annoying church officials. His approach was to argue science is not contradicting the Word of God, but helping to explain it. Kepler wasn't interested in providing an alternative explanation of the solar system than that of the Church, but instead to try to use science simply to describe the order which God had created. Even though he was still living in an era where geocentrism was favored by the Church, he set out to understand the motion of the planets around the Sun. To do so, Kepler was keen to advance the heliocentrism within the confines of biblical teachings. His first major book, in 1596, essentially tiptoed around the idea of heliocentrism by arguing that the Earth's motion in the universe was of godly order, in line with passages in the Bible. As a result, the book was nowhere near as controversial as the works of Galilei, and Kepler was allowed to continue working in this vein. As Kepler's career advanced, he continued to skirt the line of scientific revolutionary and obedient church subject. His groundbreaking works, including Astronomia Nova in 1609, Harmonies Mundi in 1619, and Epitome Astronomiae Coperniconiae in 1621, redefined and ordered the solar system in ways that would be critical to the coming European scientific enlightenment. Kepler's defining contribution to astronomy, planetary science, and space exploration are his 3 laws of planetary motion. The first of these laws is really quite simple. The orbit of the planets around the Sun are ellipses, that is to say, oval-like. An ellipse has 2 foci, unlike a circle which has 1 foci in the middle. Before Kepler, heliocentric models assumed circular orbits around the Sun. Kepler's first law was based largely on his observations of Mars, which clearly pointed to elliptical orbits. However, what's missing from Kepler's laws is a clear causal mechanism for this elliptical orbit for the planets. What Kepler could not have known, as Newtonian physics and gravity were not yet articulated, was that the elliptical orbit of the planets was an indication of the significant mass difference between the Sun and all of the planets in the solar system. Kepler's second law is a bit less self-evident than the first. In fact, while it is a fundamental aspect of understanding planetary motion, it is not something too many people may think about or even know about. Kepler's second law states that if you were to observe a planet-sun relationship from above, with a sort of bird's eye view of the solar system, and draw a line from the planet to the Sun, the area that the line would cover would be the same for any 2 equal periods of time of travel along the planet's orbit. What is this saying then? Remember now that orbits are not circles. For example, the Sun is not at the middle of the Earth's orbit. The Sun is on one side, or acting as one of 2 foci of an ellipsis, or oval. This means that some part of the Earth's orbit bring it closer to the Sun than others. In the diagram, Area 1 is a triangle made up of 2 points in the Earth's orbit in which it is closest to the Sun, or what the Greeks would call perihelion. Area 2 is made up of a triangle with 2 points along the Earth's orbit when it is furthest from the Sun, called aphelion. Critically, the 2 points of the orbit creating both triangles are 30 days apart, even though the points in Earth's orbit used for Area 1 are further from one another in space than the ones in Area 2. Ultimately, this all means that a planet moves faster along its orbit when it is close to the Sun than when it is further from it. This also means that for something with a highly eccentric orbit, say a comet, that comet will move along its orbit orders of magnitude faster when it is close to the Sun than when it is out in the furthest parts of the orbit. This is what happens with Halley's Comet, which can only be seen from Earth every 70 years or so. When Halley's Comet is out in the outer solar system where we can't see it, it is traveling incredibly slow compared to when it comes in closer to us. When it comes into the inner solar system, where Earthlings can see it, it speeds up and barely spends any time in our neighborhood at all, quickly off to spend another 60 or 70 years in the outer solar system. This change in orbital speed is one thing, but for Kepler to have recognized that speed is exactly correlational to distance from the Sun, and therefore that equal areas are covered in equal time, is miraculous, given that he was working with pre-Newtonian physics and no consolidated theory of gravity. Moving on to Kepler's third law, it is again, like the first law, a bit more simple. It states only really that the further an object's average distance from the Sun, the longer it will take to go around the Sun. This was another systematic order of the solar system that Kepler discovered. The Earth, for instance, takes 365.25 days to go around the Sun. Kepler noticed that Mercury and Venus, nearer to the Sun, took fewer days to complete their orbits, while everything further from the Sun took more Earth days to complete one orbit. Again, it wasn't just recognizing this difference in orbital periods, or years, but also the mathematical relationship that lie beneath. The square of a planet's orbital period is exactly proportional to the cube of the distance of the planet's semi-major axis. Or, more simply, the further an object is from the Sun, the longer it takes to complete one orbit around it, and that there's a direct relationship between distance and this orbital period. And this is what is so important about Kepler's laws. They are not only observations, they are empirical, that is to say, mathematically confirmed and predictable, repeatable. And though Kepler didn't have the tools to finish the puzzle by confirming and explaining causal mechanisms, again, he couldn't have known of gravity, his three laws remain not only true, but indispensable in the work of modern scientists who send spacecraft, that Kepler could have never imagined, on rendezvous paths with the very planets he eyed through a telescope. These rendezvous paths are only possible due to our understanding of planetary motion. Before we wrap up this first part on our understanding of the solar system before the space age, I want to provide a quick honorable mention to Joseph Louis Lagrange. Lagrange was a French astronomer who discovered something that today bears his name, Lagrange points. Lagrange points may have been identifiable to Copernicus, Galileo, and Kepler, but without an applicable theory of gravity at their disposal, it would have been nearly impossible to make sense of them. So what are Lagrange points? In short, they are gravity traps. As you may know, all physical bodies in the universe attract other bodies, a phenomenon critical to the theory of gravity. Well, if two objects are pulling on one another, there will be a point in between in which a third object would be tugged equally on both sides of it. If in space, essentially it would sit still. In 1772, Lagrange published Essay on a Three-Body Problem, in which he detailed the gravitational mechanisms of this process and the very messy gravitational environment of our solar system. Eventually, this led to him identifying 5 types of Lagrange points within any two-body system. As I explain these, look at the diagram and imagine a small asteroid in each of these points, with the Sun and Earth both pulling on it. L1, or Lagrange point 1, is between the two objects, but closer to the smaller one, Earth in our case. Now, if the gravity of the Sun is so much more powerful than the gravity of Earth, you may be asking yourself, why doesn't the much bigger Sun win in this scenario and pull the asteroid in? Why would it stay in L1? The answer is distance. The L1 point is created where the smaller body has just enough force to withstand the pull of the larger body. Naturally, this proximity to the smaller body acts to even out the gravitational advantage of the large body. L2, oddly enough, is actually on the outside of the smaller object. This may seem counterintuitive, but essentially, in our example, the gravitational force of the Sun and Earth are keeping the asteroid from slinging away. L3 is essentially the opposite of L2. L2 and L3 are a bit odd, so don't beat yourself up if they don't immediately make sense to you. Another way of looking at L2 and L3 is to think of them as stable orbits around the Sun created by the Earth's presence. L4 and L5 are simpler. L4 and L5 are parts in the smaller body's orbit around the bigger object in which objects can fall into or get trapped. In some way, this is a gravity well, either in front of the smaller body's orbit or trailing behind it. We can see L4 and L5 Lagrange points in action in our solar system by looking towards Jupiter. In the Jupiter Sun L4 and L5, there are a host of trapped asteroids that are stuck following or leading Jupiter as it orbits the Sun. These asteroids can't escape this orbit as they are locked in place by the dueling forces of Jovian and solar gravity. These kinds of asteroids in our solar system are called Trojan asteroids, asteroids that camp in the orbits of two bodies. They're named so because the asteroids discovered in Jupiter's L4 and L5 locations are all named for characters from Homer's Iliad. So I hope you have an appreciation of how the current vision of our solar system began long before the space age. As you watch what's happening on screen, recognize that much of the understanding and discoveries made by the people we just discussed is underscored by advanced mathematics, observations, and empirical evidence that can be duplicated by any observer with the necessary knowledge and equipment. While it's wonderful to recognize the general simplicity of our solar system, as we've done here by covering the basics, actually launching things into it to the right places at the right time with the right speed and avoiding all the messy gravitational interactions you can see on screen is an incredible feat. Of course, to do that, we need rockets. And just like heliocentrism, rockets didn't come out of nowhere in 1957. No, they too have existed since long before the space age. So this concludes part one of Before the Space Age. Now we're going to talk about rockets, the greatest and worst thing humans have ever invented. Again, as with the history of basic astronomy that we just covered, I can't cover every minute advancement in the history of rocketry, but I do want you to understand that rockets are both old and were first invented for war, not exploration. We'll talk a little bit more about rockets when we cover the space race and the Apollo program, but after that we're all good. This isn't a rocketry or an aerospace course, but I do think the basic history of rockets is worth understanding as it provides helpful context on the origins of the space age. The exact origin of rockets is, as you can imagine, unclear because it was so long ago. Sometime in the late 10th century, Chinese militaries were experimenting with projectile devices. Very simply, they were filling bamboo tubes with gunpowder and pointing them at their enemies. By the 13th and 14th century, rockets were becoming increasingly popular among military leaders in China, and their ability to set fire to opposing military bases or structures was catching the interest of other nations. It's difficult to do justice to the spread and development of this initial invention, so I won't even really try here. But long story short, the earliest documented use of rocket technology comes from 10th century China. Moving forward several centuries, one of the most noteworthy advancements in rocketry is the early use of metal to build more reliable rocket tubes. The Mysorean Kingdom, now in India, advanced rocket technology considerably by adding an iron casing to wooden tubes. These rockets were used to ward off attempts at British colonization in the 1790s. And here's where rocketry is picked up by Western imperial powers. It's likely that the retrieval of some of these Indian rockets by defeated British armies led the British to copy the technology and use it as a weapon of colonial violence, as well as in wars with competing empires, notably during the Napoleonic Wars of the early 19th century. British military figure William Congreve copied many of the ideas of the Mysorean rockets to develop what became known as Congreve rockets, the first full-metal, finely formed rockets. The technology was spread to British allies during the Napoleonic Wars, where it was famously used in 1812 by the Russians to defeat the French. At the same time, rockets saw limited application in North America during the War of 1812 between Britain and the United States. In this instance, their use influenced the line, "and the rocket's red glare," in a famous American poem that would eventually be incorporated into the national anthem of the United States. In 1903, a Russian school teacher named Konstantin Tsiolkovsky published a bizarre paper called Exploration of Outer Space by Means of Rocket Devices. The work laid out how a rocket could achieve speeds to actually escape Earth's gravitational pull and enter outer space. Tsiolkovsky's work was pioneering, as while rocketry had been advancing at a rapid rate since the end of the Napoleonic Wars, there was little discussion of the idea of rockets that could leave Earth. With this paper, Tsiolkovsky came to define what would become a critical idea in the lead-up to the space age: escape velocity, the speed and direction a rocket would need in order to reach outer space. Not only did Tsiolkovsky develop the notion of a rocket going to space, he combined advances of rocketry with an old idea from Isaac Newton. Tsiolkovsky, like any physicist, knew that gravity operates equally on all objects, regardless of their speed. For example, if you hold a bullet in one hand and a pistol in the other, then fire the pistol at the same time as dropping the bullet you're holding, both bullets will hit the ground at the same time. The only difference is that the bullet that was shot out of the pistol will have had forward velocity during its descent and therefore have traveled some distance away from the shooter during its fall. But from gravity's perspective, that speed doesn't matter. The bullet was brought to the ground just as fast as the other. The same would apply for rockets, and this is why the notion of horizontal speed of an object came into play in Tsiolkovsky's work. Building off of a famous thought experiment called Newton's cannonball, Tsiolkovsky calculated the speed an object would need to not only leave Earth, but also be able to stay in orbit, thus reaching a state where its speed of travel away from the Earth matched the rate at which the Earth was trying to pull it back down. So the object is being pulled back down to Earth, but because its forward movement is so fast, by the time it should be hitting Earth's atmosphere, there is no more Earth underneath it to fall into because it has moved forward away from the Earth.
To show how gravity works on Earth and in the skies, Newton designed a thought experiment. He imagined firing a cannon from the top of an extremely tall mountain. From his first law of motion, he knew the cannonball would travel in a straight line at a constant speed forever. But gravity pulls the ball downward. If its speed is low, the cannonball hits the Earth near the mountain. The higher the speed, the farther away the ball lands.
If you throw it faster, it comes farther away. Even faster, farther away. Even faster, it may go 1,000 miles. Even farther, it may actually go almost halfway around the Earth and there hit the Earth.
Newton imagined that if its speed were high enough, the cannonball would travel all the way around the Earth and settle into orbit.
The orbit of the cannonball around the Earth was a balancing act between the cannonball's tendency to fly off in a straight line and its being yanked back towards the center of the Earth continuously by the force of gravity. So in Newton's picture of the world, there were two things. The natural tendency of an object to travel in a straight line, which was true on Earth or in space or anywhere, and there was the attraction of gravity, which was true on the surface of the Earth, and it was true up in space.
Newton's breakthrough was to see that the moon's orbit around the Earth and a cannonball's motion on Earth were governed by the same law of gravity.
Tsiolkovsky's works became definitive in the study of rocketry, though not everyone was convinced that a rocket could reach outer space or sustain speeds needed to enter orbit around the Earth. In the 1920s, U.S. physicist Robert Goddard built and launched the first liquid-fueled rockets. Goddard was heavily criticized for his ideas that rockets would be able to leave Earth and travel towards objects like the moon, as it was assumed that a rocket wouldn't work in space because there was no atmosphere to push against. This was a fundamental misunderstanding among a few at the time, that a rocket's propulsion was dependent on pushing against the atmosphere. More accurately, we know that rockets are propelled in space and on Earth by having their forces push equally in all directions of the rocket except the rear, or that a rocket pushes itself every direction except backwards. You can imagine a rocket as a bomb that is exploding. When the bomb explodes, energy is expelled equally in all directions. If you put that bomb in a tube and then leave one end of the tube open, energy will press against the sides and front of the tube, but not the back, creating forward motion by sort of self-propulsion. Goddard ran successful tests, but was never able to reach space. For his trouble, NASA named many things and stuff after him. In the 1930s, a young German rocket scientist named Wernher von Braun developed ideas to scale up Goddard's designs in order to reach higher altitudes, further distances, and eventually outer space. Von Braun was inspired by science fiction to develop the means for space travel and become an astronaut himself. His singular concern with developing rocket technology unfortunately coalesced with the rise of fascism in Germany, and before long von Braun was working for Adolf Hitler's regime to develop rockets for military purposes. Nazi funding and resources, including concentration camp labor, led to the construction of A4 rockets, the scaled-up version of Goddard's designs that von Braun had dreamt of for years. The A4 rocket evolved into the V2 rocket, the tool that Hitler and the rest of Nazi command hoped would win them the war. However, by late 1943, by the time the rockets became operational, the tides had already begun to turn against Nazi occupation in Europe and World War II as a whole. Nonetheless, Nazi offense versus the English in the later part of World War II consisted of hundreds of V2 rockets launched from mainland Europe at London and other urban centers in an attempt to weaken the United Kingdom before an eventual Nazi ground assault that thankfully never came. Thousands of English civilians were killed by V-2 rockets during the latter part of the war, but the rockets' applications did little to achieve military objectives for the Nazis. At least 10,000 people died making the rockets at concentration camps across Nazi-occupied Europe, where mostly Jewish Europeans were starved, tortured, murdered, or left to die in disease and inhumane conditions. All of this history is a disturbing part of space exploration's past. Amidst this human suffering, a Nazi-launched von Braun-designed V-2 rocket became the first human-made object to enter space. It did so on June 20th, 1944, reaching an altitude of 176 kilometers above the Earth's surface.
You are watching captured German films of the top-secret Nazi research center at Peenemünde, a base on an island in the Baltic Sea. It was here that German scientists developed the first rocket to travel faster than the speed of sound. When it was unleashed on London, it gave no warning of its approach. You heard the explosion before you heard the sound of the missile. The results were devastating. Leading the German research was Werner von Braun, a scientist whose passion about space exploration was exploited by the Nazis. Years later, von Braun would work for NASA on the Apollo missions, but now his focus was on London. The German project had its share of successes and failures. As can be witnessed here, the 2,000-pound warhead could cause a great deal of damage. At first, London felt its wrath, but now individual rockets had names such as Washington, D.C., Philadelphia, and New York. Those were the ultimate targets. It was only a matter of time before the range of the rockets would be extended from across the English Channel to across the Atlantic. But Allied bombing combined with the loss of launching sites in Western Europe following the D-Day invasion doomed Germany's chance to maximize the use of these weapons of terror. Hitler believed he could salvage the war with these rockets. More than 10,000 were fired at the Allies. They did cause initial panic to Londoners when first introduced, but they had little military impact on the course of the war. For the Nazis, it was too little, too late.
After the war, V-2 missiles and their components were collected by advancing Russian and Allied armies who wanted the technology for their own military objectives. However, it was not only the technology that was highly coveted. As soldiers liberated cities throughout Europe, scientists and engineers who had been part of the Nazi war effort surrendered to incoming armies with the hope of providing their services to new interests in exchange for leniency. As part of Operation Paperclip, the United States military arranged for the immigration of hundreds of German scientists and engineers who had served the Nazis to contribute to American weapons programs. One of these individuals was von Braun. Exploring his post-war options, von Braun's main commitment remained to work for whoever he thought was most likely to fund his rocket development ideas. Collaborating with von Braun and other German scientists, the U.S. was able to build redesigned V-2s and reach outer space themselves as early as 1946. Von Braun even went on to become a sort of popular science celebrity, working with Disney to promote the idea of space exploration to children via TV specials. Von Braun's ultimate objective was to scale up his V-2 to a larger rocket that could not only reach space reliably, but put satellites and even people in orbit or on the moon. Von Braun would achieve these goals over the next 3 decades with the Jupiter and Saturn rocket programs that would take American astronauts to the moon in the Apollo program. However, von Braun never showed any remorse for the Faustian bargains he made, or the reality that his wartime rocketry advancements were facilitated by torturous and murderous conditions in Nazi concentration camps. Like many Nazi collaborators, to this day, his legacy remains debated. Now, stepping aside for a moment from the main story, we've heard a few times about the idea of an object entering outer space. Well, what does that mean? It's not as simple as you think. The Earth's atmosphere doesn't just stop. Instead, it slowly thins until no or very, very, very few atoms are present. So how few atoms is no atmosphere? Well, it's been debated for a long time. The reason is that there are a minute number of particles detectable for a good while when heading away from Earth. But does one atom per trillion or trillion billion still count as an atmosphere? Currently, a mostly accepted definition of where space starts is the von Karman line, named after Hungarian engineer Theodor von Karman. The idea of the von Karman line comes largely from calculating the resistance faced by objects in flight at different altitudes above the Earth. For a variety of reasons related to atmospheric chemistry that we don't need to worry about in this course, a convenient 100 kilometers above mean surface level altitude is now accepted by most physicists and space agencies as the so-called beginning of space. Returning to the story, von Braun wasn't the only dreamer of spaceflight who was developing rockets at the time. In Russia, there was an engineer by the name of Sergei Korolev. Korolev's designs also built off of both Goddard and a close inspection of reclaimed V-2 rockets. His work would lead to Russia's R-7 rocket program in the late 1950s. Like von Braun, most people interested in Korolev's work were political and military officials wanting new weapons. Unlike von Braun, Korolev was not made a celebrity and a public communicator for the wonders of spaceflight. Instead, his existence was kept secret by the Soviet Union that governed Russia and much of Eastern Europe at the time. While Korolev knew of von Braun working in America, von Braun had no idea his Soviet counterpart even existed. It was in a fateful meeting between a then unknown to the world Korolev and Nikita Khrushchev, the premier of the Soviet Union, that the seeds of the space age's genesis were planted. During an inspection of the R-7 factory in 1957, Khrushchev was impressed by the size of the rockets and the promises by his engineers that rockets able to hit Washington or London would be developed within a few years. It was during this meeting that Korolev took a stunning risk. At the meeting's conclusion, he requested a moment of Khrushchev's time. There, in the factory, Korolev led the premier and his entourage to a table upon which two halves of a small silver sphere were sitting. Korolev explained that this device could be welded together as a sphere with a small radio inside and an antenna on the outside. It could then be mounted on top of an extra R-7, not needed for military purposes, and launched into outer space. Given the weight of the object and the power of the R-7, the object would enter space with enough speed to go into orbit around the Earth and send back messages from its radio. Khrushchev, initially skeptical, was intrigued when he was told that the object's polished metal exterior would make it glow in the night like a shooting star, visible from Earth, anywhere on Earth. When it was explained that this would mean Americans would not only hear the radio transmissions from space, but see for themselves that Russia had put an object in orbit, Khrushchev was convinced. Korolev was granted an R-7 rocket for his little science experiment, as it was called. The premier's office prepared for what they thought would just be a minor propaganda win, and the space age had begun.
This man stands on the threshold of outer space. It's the biggest story of the year, possibly the #1 story of the century. This launching of the Russian satellite, which brings into the realm of possibility all those wild science fiction stories of interplanetary travel. Watch it. It's fascinating. This animation is a graphic portrayal of how a satellite operates. This story of the Russian satellite burst upon a startled world early in October. Russia announcing she had shot a man-made moon 560 miles into space, where it was circling the Earth at the dizzy speed of 18,000 miles per hour. It sent its familiar beep-beep back to Earth, was tracked by radio and by sight as it hurtled across the heavens. The satellite was launched as part of IGY, the International Geophysical Year, a gigantic study of the Earth and its surroundings by 64 nations from both sides of the Iron Curtain, in common effort to benefit mankind.
On October 4th, 1957, Sputnik entered orbit around the Earth. It would stay there for 3 months, circling the Earth 1,440 times before its speed reduced enough for the Earth's gravity to pull it back down. Sputnik not only kicked off the space age as the first human-made object to orbit the Earth, it started a narrative of competition between America and Russia that would run for almost 2 decades and be known as the space race. Khrushchev's people were dead wrong. This was not a minor propaganda win. It was a propaganda goldmine. American newspapers lamented Soviet technological superiority, and congressional meetings were immediately called to address the subject, as everyday Americans stood outside each night to see the artificial Russian shooting star fly over their heads. In this so-called space race that emerged, space technology was a proxy for military might and technological and ideological superiority. The nation that could put the more advanced space missions together was the nation that was to be seen as winning the space race, at least by some. Sputnik was launched on a whim. It was a humble craft with no more than a small radio transmitter inside of a beach ball-sized metal sphere. The ramifications of Korolev's little science experiment would lead to humans in space, humans on the moon, and a new age of space exploration where our solar system was no longer studied through telescopes and the rough sketches of wealthy astronomers. Thanks to the success of Sputnik, our solar system neighbors were about to get a lot more visitors. So there you have it, many centuries of activities jammed into one lecture from 4th century BC to October 4th, 1957. That's where we end this lecture, and that's where we'll pick up next week with the space race. But I hope you understand that the space age didn't come out of nowhere, that our knowledge of the solar system is centuries old in many different ways from around the world, from ancient Greece to the golden age of Islamic knowledge, to Renaissance Europe and everywhere in between and beyond. So our knowledge has built up over centuries. That goes too for space technology, and all of this matters for how things move forward. Obviously, the discoveries of people like Kepler and Avampas inform how we explore the solar system and what we're able to do, and the history of rocketry and its intersection with things like World War II influence the way the space age unfolds and the way people think about space exploration and the way people look at what's happening and make decisions about it. So all of this matters and influences space exploration moving forward. So it's a little bit of historical context. We'll continue that historical context, obviously, with the space race, but I hope this really shed some light and kind of did away with some misconceptions people can have about when we learned about certain things about the solar system, or when the space age started and where that technology came from. So with that, I hope you enjoyed, and we'll see you next week.